You're listening to two girls, Svetlana and Christina, busking and live streaming on a street of Zaporizhia on the 9th of August this year, raising money for the Ukrainian army. This was their last song for the day, but it also turned out to be their last song. After finishing the set, the girls went for a walk, and a Russian missile fired at the city took their lives.
Слава Україні!
Hi, welcome to the bioinformatics chat. I have two guests today. It's Dominik Kempa, who is assistant professor at Stony Brook University, and Tomasz Kociumaka, a postdoc at Max Planck Institute for Informatics. And we will be talking about their recent paper that's called Collapsing the Hierarchy of Compressed Data Structures, Suffix Arrays in Optimal Compressed Space. So guys, welcome to the podcast. Very excited to talk to you.
Thank you very much. Thanks for inviting us.
Hi, thanks for having me.
Let's start with your scientific careers, your paths, and how do you guys know each other?
So I started as a PhD student at University of Warsaw. Then I was a postdoc at Bailan, Israel, at Berkeley, California, and now in Germany, in Max Planck.
And what did you study?
I studied computer science at all three institutions.
So I did my PhD at the University of Helsinki. Then I was a postdoc at University of Warwick in UK. Then UC Berkeley, then Johns Hopkins University, and now I'm an assistant professor at Stony Brook.
Okay, and so you're both like theoretical computer scientists, but was your focus always on data structures?
Personally, I've been doing string algorithms since the beginning of my research career. It's not only data structures, it's also more algorithms like fine-grained complexity, even things like quantum algorithms. So it's string algorithms, but from various perspectives, and data structures is just one of them for me.
For me, string algorithms were always the main focus. I already, going into my PhD, I already knew what I wanted to do. I chose the PhD that I could do string algorithms, and then I continued on with this all the way through my postdoc years until now.
And so for a lot of people, the motivation for working on string algorithms comes from bioinformatics. Was that one of the reasons why you chose to look at them? Or what are the applications that you were looking for, if any?
So definitely bioinformatics is like the area that drives nice questions you can work on. Like the way I got engaged into this area is more like a coincidence. I was participating in some undergrad course on text algorithms, and I ended up liking it. And I started collaborating with the professor delivering the lecture and some of the assistants. But bioinformatics came later, and it still serves as an important application and source of problems.
For me, it kind of was my favorite subject. When I learned about algorithms, I tried to understand some different areas like geometry, graph algorithms, and string algorithms. And somehow I was drawn to string algorithms because it felt that I could kind of understand everything. It was so nice and discrete that it just became my favorite area. I was really fascinated by the beauty of data structures like suffix array and suffix tree. So yeah, that's how it started.
Okay, and how did the two of you meet? And did you collaborate before, or is this your first collaboration?
No, so we started working, I think, in something like 2018, where we had like the first paper, which was the construction of Barrow's-Wheeler transform in better runtime. And initially, we've been mostly working remotely. Then we've been at Berkeley for some time, and now we are again working remotely. But I think we've met at some conferences for the first time.
Yes, I think so. We definitely met before, probably a couple of times. But yeah, we started working quite recently.
All right. And so your paper is, first of all, about suffix arrays and suffix array queries. So what are the suffix arrays?
So the suffix array is a data structure that's used to answer some pattern matching queries on a string. The data structure is defined in a very simple way. So you take your string, you list all the suffixes of the string, so all the fragments starting at any given position and going all the way to the end of the string, and then you sort those suffixes lexicographically. The suffix array then lists the starting positions of the suffixes, but the positions are in the lexicographic order of the suffixes.
And why is this data structure important? What kind of things does it allow us to do?
So perhaps the most famous applications is the pattern matching queries. So you build a data structure for your long string, and then at query time, you can answer whether a shorter string called a pattern occurs anywhere within the long text. So that's the basic application that's motivated the beginnings of a suffix array. By now, people have used suffix arrays and related suffix trees in dozens of other applications. So that's why simulating suffix arrays was an important problem.
Okay, can you give us some other applications?
So, for example, matching statistics is something that's been used, as far as I know, quite significantly in bioinformatics. Then it's not only exact pattern matching, it's also used as a tool within approximate pattern matching algorithms when you allow some edits between the pattern and its occurrences.
And so your paper is specifically about compressed data structures, right? And so one way we can store a suffix array is just a plain array. So if we have a string of length n, we can just store n numbers, right? So for a sequence of 3 billion letters, that would be an array of 3 billion numbers. But a compressed data structure means that you can store it more efficiently and yet still perform the queries, right? So how does that work?
So there's a whole hierarchy of these compact and compressed data structures. So the plain representation, as you have said, takes n integers. In each of these integers, it is like 16, 20, in this case, it's like 32 bits, for example. Then there are data structures like FM index or compressed suffix array, which can squeeze it so that the suffix array implementation takes space roughly the same as the text itself, which is much smaller if the alphabet is small. Like in bioinformatics, we usually have 4-character alphabets, so you can spend just 2 bits per character.
I think that this is a very important point that I want to focus on. So even though like theoretically both arrays, so the array of letters and the array of numbers are like of the same length, but an integer just takes more, like if we look not at the asymptotics, not at the abstractions, but at the concrete number of bits, right? Then an integer takes more space than a one of 4 letters, right? And so it pays off to store that not as an array of integers, but as an array of the same length, but of letters.
Yes, exactly. And also in theory, we can model that because like any entry of the suffix array requires log n bits, while if the alphabet is smaller, like of constant signs, it's just a constant number of bits per character. Yes, so this was the second level of the hierarchy when you have data structures taking as much space as the text does in its plain representation. What we are focused is a data structure for text for datasets which are highly compressible. So you take some compression algorithm like lempel-zip, for example, LZ77, and we want a data structure whose size can be bounded in terms of the compressed size of the input data.
So you mentioned lempel-zip. Correct me if I'm wrong, is that the algorithm behind the gzip tool, so that it's more familiar to people under that name?
Exactly. It's one of the key components of gzip.
Like you can think about it as like running gzip on a suffix array, or is it gzip on the original text?
It's on the original text. On the original
text. Right. And still you can run the queries on it, right? So it's a fully, like you don't have to decompress it. Normally we have to decompress stuff to work with it, right? When we compress something with gzip and we want to edit it, we have to decompress it. But here it's compressed and you can still run queries against it.
Mm-hmm, yes, so you can view it as kind of a custom compression format, which is not much larger than gzip, but still allows you to access the suffix array of your data.
Right. And let's talk about the hierarchy. So the hierarchy goes in terms of like, on the one hand, you have the power of a data structure, like what kind of queries it can answer. And on the other hand, you have like how much space it takes, right? And so normally the powerful the data structure is, probably it will require more space, right? That power comes at a price. So let's talk about the hierarchy. Like on the one end of the spectrum, there are suffix arrays, right? What's on the lower end of the spectrum? What are some less powerful data structures?
So the hierarchy, the sort of the lowest end of the hierarchy would be occupied by data structures supporting the simplest queries, in some sense the least powerful queries. And the kind of query that is often understood as the least powerful is random access. So this is the kind of query where, given a position in the text, the query simply returns the original character, the character at that position. So you can kind of see that if you can support that sort of query, you can decompress fragments of text, but it doesn't, for example, let you search. Whereas a suffix array is more powerful in the sense that you can use it to do pattern matching.
Okay, and we should clarify that, trivially, if something allows random access, then any other query is allowed by just decompressing our text, right? But the difference is in the time it takes to perform the operation. So what kind of sort of bounds are we imposing to say that some index supports some query?
So usually we would say that polylogarithmic in the length of the input data is like the threshold between data structure supporting some operation or not. Obviously, we would like this polylog to be as low as possible, but that's like the first approximation for it to be a polylog.
Okay, and polylogarithmic means what exactly?
So it's a logarithm of the input size to some finite power.
And so to give even more intuition about this, sometimes we can even think of a logarithm of something as like almost a constant, right? Because the logarithm grows like very, very slowly.
Yes.
Yes, that's true. I mean, logarithms are generally considered a very slow-growing function, and therefore, if you can support something in logarithmic time, this will really run quickly in practice. And sort of the assumption is that because of that, then when you also raise the logarithm to some fixed power, like square it or raise it to a third or fourth power, that's still going to be fairly efficient.
And so you mentioned that on the lower end of this hierarchy, there's just random access. So can you give us like some names? What are the data structures that support those queries?
So for this compressed regime, I think that something called the block tree is currently the best data structure for random access itself. It's also much, much simpler than what we are doing. And of course, if you go beyond the compressed world to this compact and so on, then you can just have the plain representation which supports random access, unlike the suffix array implementations in this compact space, which are already sophisticated data structures.
And so what are the things in the middle that you can mention? Like there's suffix array queries, there are random access queries. What are some things in the middle?
So perhaps the two things in the middle would be something called lowest common extension queries, which basically ask you to find how long can you go from two positions in the text before you encounter a mismatch between them. So it's also very closely related to just queries asking whether two fragments of your input data are equal or not. If you binary search on top of that, you will be able to find the first difference. And another thing in between would be the pattern matching queries, which we discussed. So suffix arrays has pattern matching is one of the applications, but it has also many other applications whereas pattern matching is just a single problem. So that's why it's an easier query.
And when we say it's a hierarchy, it means that, for example, suffix array queries allow us to perform all those things, right? They allow us to perform random access. Can you describe, like in simple words, how that works? How having suffix array allows us to just look up any character?
So in this case, you can indeed do that. So in the suffix array, the suffix array sorts all the characters lithographically. So if you want to have random access, you just need to remember the thresholds where the first character of your suffix switches from one character in the order to the next one. If your alphabet is very small, this is just a few numbers. And if you record those numbers and then ask for the rank of your suffix in the lithographical order, which is what we call the inverse suffix array query, this would give you the character at the position you're requesting.
Well, what is the relationship between the suffix array and the inverse suffix array? So the on the one hand, the relationship is that they're just inverses of each other, right? In mathematical sense, I guess they're inverse functions. But if you have one sort of query, does it automatically allow you to do another, or do you have to store sort of both versions?
Our data structure, at least, we kind of have to support these two operations separately. At least in that compressed setting, we support them separately.
Mm-hmm. So having one sort of doesn't guarantee the other.
I'm wondering now if we can simulate one using the other. I'm sure if not, it's not possible in one direction. I don't think so right now, actually. I don't think so.
All right.
Yeah, we support kind of them separate. In our paper, there's basically a separate description of inverse suffix array query, and then suffix array query is slightly different.
So you would say they occupy sort of the same level of the hierarchy, just they're sort of horizontally arranged.
Yes, I would say that, yeah.
Okay. And so the main point of your paper, I think, is you say there is no hierarchy, right? You propose a data structure that occupies as little space as the bottom of the hierarchy, and yet is as powerful as the top level of the hierarchy. So I guess my first question is, how did you discover it? Like, did you know in advance that this would be possible? Were you working towards it, or did you discover it by accident? Were you surprised that it's possible?
I think it's quite surprising to me that this result turns out to be possible. And whether or not we knew it, it's hard to say. This result is really an effect of working with this problem for the last 5 years, and we were slowly getting better and better results. We had some kind of earlier results related to suffix arrays in the last few years, and at some point we realized that this result might be possible, and then we worked on it for a few months, and in the end it turns out that it all worked. So
yeah, so like also in the meantime, since we have started working on the suffix array, also the state of the art for random access has improved, so you have to catch up to like the state of the art for the other end of the hierarchy, but this turned out still possible.
Mm-hmm. You mean the space that the random access data structure occupies?
Yes.
But I think in your paper you say that there is a lower bound, right, on that space. So was that lower bound just not known before, or
so the way we express the size of the data structure is with some measure of repetitiveness that is called substring complexity, and it's been like, I mean, I wouldn't say discovered, but it was made popular only in the last few years. Like I think the journal paper was in 2022 and conference version in 2020. And it has this nice property of unifying, in some sense, many other compression measures. Like it's a lower bound for the size of lempel-zip compression. So you think gzip is a lower bound for BWT-based compressions, which is like bzip2, for example. And if you specify your space complexity as a function of this measure delta, then indeed the space complexity of our data structure is probably optimal. So in the worst case, you cannot have any better dependency on this delta and on the length of the text.
And I'm curious, when you arrived at this result, when you sort of invented or constructed this data structure, were you confident enough that it all works out, or would you like implement it in code just to be sure that everything works? Or is it just pure math for you?
I mean, implementing in code would be a much bigger undertaking than writing down a paper, I would say.
So you haven't actually implemented it yet?
No.
Interesting.
Also, because we are using some other components, some small data structures, for example, from computational geometry, and these data structures also haven't been implemented, so it would cause some chain of dependencies that is hard to resolve.
Wow, that is actually very surprising for me, because coming more from the software engineering world, like I don't usually trust myself unless I coded something, and here you sort of operate with notions that haven't been even implemented yet. So it sounds more like, to me, like theoretical physics, where they assume that some particles exist, but they don't actually like observe them, or they haven't discovered them yet, or something. Would you say that's a bit unusual in computer science? Like even theoretical computer science, or is it normal for you guys?
For theory, I think it's perfectly normal. So these algorithms have like the proofs of correctness, which is probably the main reason why the paper is so long, because you have to prove everything and some details get technical. And like in some sense, these proofs are stronger than implementations of correctness, because you mathematically argue that it works always, and that you don't even always know whether your test data are capturing all the corner cases. While on the other hand, it's like proof written by humans, so we are still quite far from automated proof verification in this area. So
yeah, exactly. Like, do you fully trust yourselves and the reviewers that the proofs are actually correct? Like, could it be that some error? I guess it could be, right, that some error is discovered and it just doesn't work or something.
I mean, errors happen in theoretical world. It's quite rare when the errors are serious, meaning that you cannot just change something in one paragraph, and usually these kind of errors happen quite often, and I wouldn't be surprised if there are some like indices which are messed up with one of the proofs of 130 lemmas or something. But I trust that the big picture is correct and that the components we utilize in the data structure work and so on.
And so you mentioned that you rely on some notions that haven't been implemented yet, like I think you mentioned some geometry stuff. Like, can you talk about those things?
Yes. So basically, in this paper and also in the previous papers, we reduced these problems in suffix array area to problems in geometry, which are so-called orthogonal range queries. So in this setting, you have points on a plane, and at the query time, you are given a rectangle, and now you want to, for example, count how many points are in the rectangle. And the rectangle has axis parallel to the standard axis, so it's like an orthonormal rectangle. So for here, we are using this for weighted counting. So each of these points has weights additionally. And also you don't really, the coordinates are not really integers, they are strings. So they are only given as a comparison operator in terms of how it's implemented.
So you're saying that someone already proved that these queries are possible, right? And you're relying on that.
Yeah, so these are, I guess, works from like even late 80s that we are relying on. And also this is, I think, the main reason why the power of the log n in the running time is quite large for our query algorithm, because we do rely on these geometric data structures, and it's not clear if they have been optimized to the... It's perfectly possible that these running times of these geometrical queries can be improved.
What's preventing people from actually implementing those algorithms? What's the hard part there?
I mean, it's quite a lot of effort. Usually you need to hire some students to do that, or you need to have some manpower to do that. That's, I guess, in general, there is no tradition in theoretical computer science to implement algorithms.
No, but I mean, probably if it took like a researcher one day to code it up, they would probably do it, right? So what's the tricky bit that takes a lot of time or a lot of effort to implement?
I mean, I would say just the complexity of the whole data structure. So there are many moving pieces you need to, and in some papers, people don't always go all the level of the details, like to fixing all the constants necessary and so on. So it's still quite a significant effort to go from a proof to the implementation more often than not.
Okay, so it's not that you don't know how to, or it's not like a research problem to implement the algorithm. It's just a lot of programmer work. Is that what you're saying?
Mostly, yes. Like if the paper is of good quality, then yes. And also, but it's also a research problem to optimize these implementations, because in theory, you just optimize for the asymptotic runtime, the O notation, the big O notation, and it can behave pretty differently to actual running time because of various issues like large constants hidden somewhere or some cache issues and lots of other factors.
Mm-hmm.
And I would add that quite often theory papers are written in a way that optimizes the kind of the clarity of the explanation versus detailed explanation of all the boundary cases. Although in this case, we put quite a lot of effort to describe all these details, and that's perhaps the reason why some of the proofs are so long, because we try to come up with the definitions for various arrays and sequences and functions that the data structure uses that handle all those boundary cases. And if you do that, then it is actually good for those who want to implement it, because the burden of solving all those boundary cases is already handled in the proof. So the proof is maybe long and complicated, but the implementation is actually relatively simple. And in this case, I think it's, despite the length of this paper, the data structure is not really that complex. If you look at just purely at the data structure itself, not at the proofs, like the combinatorial proofs, the data structure is really not that complex for a 100+ page paper.
Is it feasible to talk about the data structure itself, or would we get like bogged down in the details? So you mentioned that geometry data structure. Is it feasible to give the intuition of how, suffix array queries reduce to these geometry operations?
I mean, perhaps it's simpler to do it on a more toy example of pattern matching,
okay,
which is like slightly lower in the hierarchy. So because in this case, already lots of previous work have used geometry approach.
And could you clarify what pattern matching, like what kind of, are we talking about arbitrary regular expressions or just finding a substring?
Just finding substring. So at query time, you're given a short pattern, which is just a string, and you want to, in the simplest case, just decide if this occurs anywhere inside the text. You can also support counting or listing the occurrences, which is probably more useful. But for this description, let me stick to the decision version of the problem. So, for example, you can imagine some simpler compressed representation, which is similarly to how Lempel-Ziff factorization works.
And which is?
Yes, in this case, you decompose the string into phrases, and each phrase has the property that it has already occurred somewhere earlier inside the text. And this means that if you have a substring of a phrase, then it has already occurred somewhere else. So if you want to decide whether your substring is in the text or not, you just need to search it for places near the boundaries of the phrase, near the boundaries of the phrases. If it's inside the phrase, then the phrase is guaranteed to have an earlier occurrence, so the substring is also having an earlier occurrence, and let's say we just want to find the leftmost occurrence or decide if any occurrence exists. And now, when you're looking at this phrase boundary and the occurrence of the pattern, this phrase boundary splits the occurrence into the prefix of the pattern and the suffix of the pattern. So what these data structures do, they list all the phrase boundaries, and they look at the suffixes of the whole text starting there and the prefixes ending there. The suffixes are ordered lexicographically, while the prefixes are ordered in something called inverse lexicographical order. So you just read them from in the other direction, from the end to the beginning, and then treat as normal strings sorted lexicographically. And this gives you the point set. So every point you have one point for each phrase boundary, and the x-coordinate of the point is the suffix. The y-coordinate is the reversed prefix. And now in this 2D set of points, you want to find your pattern, assuming that you have already guessed or iterated over actually how does the pattern split into the prefix of this into the two parts. So if you have this anchor inside the pattern, you are looking for what's after the anchor, and it is a prefix of some of the suffixes as taken as the x-axis on the x-coordinate. This gives you the range in the x dimension, and a similar range in the y dimension comes from the first part, which is before the anchor, when you look from the anchor towards the beginning of the pattern. So that's like the high-level idea why this geometry approach is useful for pattern matching, and similarly, we make it useful for the suffix array queries.
So is your compressed representation just Lempel-Ziff encoding? So there's gzip encoding plus some details, basically?
Not really.
Okay.
So this would be this approach that I described would be too large. So this, and like one of the contributions here was to actually bring it down to this lowest possible rate. So we don't actually have phrases, and for various we have some kind of levels, which in this sense of pattern matching could correspond to patterns whose length is of various magnitudes. And for each of these levels, we have somewhat different decomposition or different anchors.
When you say it would be too large, do you mean the Lampels-if encoding would be too large, or the additional data that you would have to store would be too large?
So like the additional data, keeping in mind that we don't want to solve just the pattern matching problem, but also the suffix array problem, suffix array queries problem.
Right, because the Lampels-if encoding is optimal, right? Is basically your lower bound. But you're saying that the additional information you would have to store in order to perform suffix array queries would be too large.
Yes, like already for random access, we don't know whether it's possible to support random access efficiently in space proportional to Lampels-if. There is the best known data structure whose size you can measure in terms of Lampels-if has an extra log factor in the space complexity.
But your paper solves that, right?
Yes, so you are using a measure of compressibility which is slightly smaller than Lampels-if.
So just to make sure I understand and maybe clarify this for the listeners. So we have the lower bound, this sort of universal, right? You say in the paper that it's sort of a universal lower bound because it arrives for like a lower bound for different data structures, the delta measure. And so the Lampels-if satisfies, it corresponds to that lower bound. It's optimal in that sense, but it doesn't allow you the random access. And you propose a different data structure that is as space efficient as Lampels-if, but because it's different, it can support the queries that Lampels-if does not support.
Yes, like it could be larger than Lampels-if in some datasets, but it's always better than the best you can do in terms of Lampels-if for random access, for example.
I'm just curious, isn't there a part of you that would actually like enjoy implementing it? Don't you want to see it in action and sort of, because I know for me that would be very satisfying to see this actually working. So
I think that given enough time, a lot of these data structures in this category, including ours, I believe they will eventually be implemented. But the reason for this is something we haven't mentioned here yet, that is that in addition to the data structure, in this paper, we actually also described other result, which is the construction algorithm for that data structure. And the nice property of this algorithm is that it runs in time, which is what we call a compressed time. And what that means is that it takes as input an already compressed text using Lampels-if 77, and then it builds that data structure that supports suffix array queries in time proportional to the compressed data. So, for many data sets, the compressed input is going to already be many orders of magnitude smaller than the original text. So that construction algorithm will be very efficient. And moreover, that algorithm works not just for LZ77 compressed input text, but actually it works even if the input compressed representation is approximate. So what you can give it as input is like approximate LZ77. And this is something that's known to be computable much faster than the exact compression. So the pipeline would go something like this. You take your text, you approximate LZ77 very quickly, and then in compressed time, you convert that approximate LZ77 into our data structure, which supports suffix array queries. And then you can run with those two and potentially even more data structures that you build in compressed time, then you can run more complex algorithms. But the key point here is that there's only one step in this whole pipeline that takes time proportional to the original very long uncompressed text, and that is this initial approximation of LZ77.
And let's clarify, because it may sound that by approximate LZ77 you mean like approximating the text or some kind of lossy encoding, but you actually mean the compression that may be not as efficient as the original algorithm, right?
Yes. That's a very important point. Yes. So when I say approximate, I mean a compression that's still lossless. So that doesn't lose any of the input text. It's just that we allow the compression to be slightly larger than the optimal compression, maybe larger by a factor of 2, or up to a logarithmic factor, logarithmically larger, which is still going to be very small. But it turns out that relaxing this requirement of being absolutely optimal makes the computation much, much easier.
So given how maybe surprising this result is, the collapse of this hierarchy, did you get any reaction from the rest of the theoretical computer science community? Like, were people actually like surprised to find out this result?
So the reviews we received for this paper were quite enthusiastic, so we're very happy to see them, and this will be presented at the conference in early November.
Do you believe that this will be actually practical? Because there's still a question, right, of all the constant factors and all the practical details. Do you think that in, I don't know, 5 years, the leading bioinformatics tools would be using this approach? Or is there anything, like, are there any issues that you anticipate with the practical application of this?
And for now, the main issue, I think, is that this query time is still quite large for suffix array queries and inverse suffix array queries. So it's locked to the 5 as far as I remember. And that's, as I said earlier, due to these geometry queries. And that might be like the main factor that could lead practitioners to choose data types which are slightly larger, but still support suffix array queries in, let's say, single logarithmic time, not some larger power. In this paper, we also have like many auxiliary data structures, and something I believe for those the road to practical implementation may be slightly easier because they already have like logarithmic time. For example, our data structure for longest common extension queries, which was also already the first in this space, and this is something that I believe should be implementable quite easily and efficient.
Yeah, so I also agree with Tomek that there, we might still be a few years from these things being, widely used, but I do believe there's one aspect of this research that I think will gain more and more popularity, and this is that idea of converting between different data structures in compressed time, because I think, especially with rapid progress in DNA sequencing, we will probably soon reach a scale where the datasets are just so massive that it will just not be feasible to run these construction algorithms on them repeatedly. So I think we might only be able to afford to kind of approximately compress it once, and then it will stay in that form, and all the further processing, all the constructions of all the data structures will have to run in time proportional to this compressed representation. And this is where algorithms like ours come into play.
Yeah, and to be honest, I didn't hear much about using compressed data structures in like practical bioinformatics. I know you maybe not the right people to ask this question, but I'll ask it anyway, just in case you know. So, I mean, we talked about the FM index that is a slightly compressed version, right, of the original tags, but something beyond that, something closer to what you guys, theoretical computer scientists, research, these compressed data structures. Are you aware by any chance of any like mainstream tools that utilize these compressed data structures?
So I'm aware of a few fairly recent papers on this topic, and there's, for example, this data structure called R-index, which is being used more and more to in bioinformatics, and this is one of those data structures which achieves space, compressed space. So, but the field in general is relatively young, so I think things might change in the next few years. But there's already signs of these kind of data structures being used in practice, and as far as I know, they have been very efficient, and they really use very little space, and they're quite fast in practice.
So maybe that would be a good project for maybe some students or PhD students listening to this, like try to implement one of these algorithms and see how practical it is, how it performs, and whether it can beat any existing algorithms or indices.
Yeah, absolutely.
Yes. Also, for example, I guess one of the components that might turn out useful by itself is something that we call string synchronizing sets.
Yeah. Let's talk about that.
Which is somewhat similar to what's used in practice as minimizers. In the synchronizing sets, the main difference is that we have like proper handling of all the corner cases, including where the strings is highly periodic and don't have enough, let's say, entropy to sample fragments with the desired rate. But one of the contributions of this paper is that you can use these synchronizing sets also in the compressed regime. So these tools are not are useful there. You can, in this example that I mentioned earlier, when you are looking for the occurrences of the pattern around phrase boundaries. So in this case, the synchronizing sets let you fix just one partition of the pattern to check. So normally, in the solution I have described a few minutes earlier, you had to iterate over all the partitions of the pattern into the prefix and the suffix. And what synchronizing sets let you achieve is to just check one of these partitions. And to achieve that, you need to select some of the appropriate positions in the text, which are near the phrase boundaries, and adjust the point set for the geometric data structure. So I think this technique is one of the contributions on a more technical level, but something that I am fairly optimistic about being used also in practical applications.
Mm-hmm. And can you explain in some more detail what are the corner cases with minimizers, and how do synchronizing sets sort of fix those problems or avoid them?
So basically, the issue is that whenever you have highly repetitive fragment of the text, like in the very extreme example, you have just one single character repeated, then you cannot simultaneously select one every, let's say, tau consecutive substrings and avoid selecting all of them, because you need to do it consistently, meaning that when you select an occurrence of one substring, you need to select all those occurrences. So in the minimizers, what they are doing is they are computing a fingerprint of a substring, so a numeric hash, and what you store is the minimum in a sliding window. So in this case, for the repetitive data, everything would be a minimum for some sliding window. And what we are doing is we are very precisely defining where the minimum, where you don't need to select anything because you already know that it's periodic, and then we need to use some different techniques to answer your queries, like suffix array queries, like pattern matching and anything else. But whenever your window is at least slightly aperiodic, we already are guaranteed to have a synchronizing position or synchronizing substring. And also, our construction is deterministic, unlike the one with hashes, so it might help in some cases. And as I said, I haven't seen, at least have not been aware of any use of minimizers themselves in the compressed space regime. Mainly, possibly because then you cannot really afford iterating over all the possible candidates in the sliding window to choose the one with minimum hash. And we provide a very different construction algorithm.
Very cool. Yeah, and that's another thing to look into for more sort of practically inclined bioinformaticians. And is this notion, the synchronizing sets, is this a sort of well-known notion, or did you introduce it?
I mean, we introduced it back in 2019 paper. That's not in the compressed setting. It was just in the setting of computing BWT in just slightly faster than n time. And originally, it was much closer to minimizer. The original construction was, again, taking the sliding window and taking some fingerprints and the minima. Then we realized that this can be randomized, but the construction here is very different. It uses some kind of techniques from grammar compression. And that is relatively new, I would say, this construction.
And so going back to the hierarchy, is there anything, I guess there are a lot of things upper on the hierarchy, right? Even beyond the suffix array queries. Is there a possibility that you will squeeze some more stuff into that collapsed pancake of a hierarchy?
I think it is possible, although it becomes a lot harder as you try to support more complex queries.
So what would be the sort of the obvious next candidate that you might work on?
The next kind of sort of a very natural extension of suffix array is the suffix tree, and this has a good kind of sort of track record. Usually, if you can support suffix array, then with some additional effort, you might be able to also support suffix tree queries. That means you have to implement a couple extensions. So I think this is something that we can probably add to our data structure, perhaps in a journal version or something like that.
So is there anything else that I didn't ask you about that you would like to talk about here?
I mean, you can also spend maybe a few minutes on this measure of repetitiveness, this delta.
Sure.
Because I believe it's a nice way of quantifying the repetitiveness, and it's very easy to define. So to define this, you used so-called substring complexity function, which counts for every length how many different substrings you have of that length. And for example, whenever a substring occurs multiple times, you just count it once. Otherwise, it would be just depend on the length of your text. So if you have this function, this delta is simply defined as the maximum over all the lengths of the number of substrings of length L divided by the value of L itself. And this is a very nice and synthetic measure of repetitiveness. It's computable in linear time, and there are some works to compute it even faster or to approximate in low space and so on. And it behaves nicely when you change something in your data. So when you modify a single character or cut one fragment and paste it elsewhere, or even copy and paste, then it can increase only by an additive constant. Unlike all the more practical measures like the size of the lempel-zip itself, it can become very volatile when you do these kinds of operations like edits, like reversal of the whole string, like adding another copy and so on. And this measure lets you very easily describe how repetitive your sequence is. And then it lets you compare between how data structures perform on repetitive data. So in particular, it's one of the intermediate steps of showing the relations between the various sizes of the sizes of various the outputs of various compression algorithms. So if you've already used it, for example, to prove that one compressed representation, lempel-zip, cannot be much smaller than another, which is Barrow-Fuller transform in its run length encoded format, which is something used by, for example, the R index that Dominik mentioned, and the WT itself is also the core of the FM index. So I think this tool is also something that this work shows to be useful also in the text indexing perspective, but it's in general quite useful in comparing or transferring some results from one compressed representation to the other.
And this measure is called delta, right? And that's part of the name of your data structure, the delta SA, right? Or delta suffix array. So is that because just it was useful improving your results, or what part does it play in like your data structure?
So we use it basically to define this hierarchy itself, because the way we choose to because you can, if you say that your data structure should have compressed space, you need to choose which compressibility measure you are referring to. Like on the one extreme, you could use something very theoretical, like Kolmogorov complexity, which is not computable at all, so probably that's a bad choice. On the other, you could choose one of the compression algorithms, Lempel-Z, parallel Fourier transform, and so on. But then is the question, okay, why you have chosen this one, not the other? And here, delta lets you unify this landscape. And also, there are several ways to unify the landscape, but this one gives the strongest results. So it's the strongest lower bound we know. And still, it's useful in analyzing the complexity of our data structure. So we can bound it in terms of this delta, and it would be probably more tedious to analyze it directly using the size of Lempel-Z for the size of Barrow's Fourier transform, for example.
Very cool result, guys. And I'm looking forward to seeing all the bioinformatics papers that utilize it in some form. Thank you for coming to the podcast.
Thank you very much.
Thank you.